Okay, Maddie, can you hear me? You're connecting to audio. Okay. Can you hear me, Mads?
Yep, I can hear you.
Okay. How you feeling?
Well, I don't get how I always get food poisoning, so not great.
Not great. Okay. Well, if you feel like you need to sleep 40 winks in the middle of this, just it'll be recorded. So feel free to do so. I won't be offended.
Okay, thank you.
Our DC has a pretty good record with food poisoning, but I'm very glad the Spring Arbor Cafe closed because their record was awful. I think I got food poisoning there once. Oh, yeah, but there's a dude that says. Oh. Cooper. I'm assuming he's going to come. And he's just a tad on the late side. Okay. More dead trees. Well, it's supposed to snow again, but it looks like it's light.
Yeah, very light, so
And
that'll be fine.
Thursday looks like it's a bit more, but it doesn't seem, at least from satellite, it doesn't look like it's as big a storm.
Yeah, as long as it's just like a little bit, it's fine, but
The time it took for them to get all that snow removed.
I mean, like at my house, there's still quite a bit of ice everywhere,
Yeah.
so.
The trail on the way up to Lime Lake, there are sections of it where it melted and then the water
Yeah.
accumulated and then it just froze. So, and you can't see it. So if you're walking, all of a sudden, "Ooh." Good morning, everyone. So we're going to be a little warmer today. Forecast says snow, but I don't anticipate us getting a lot of snow. So we are talking about drug biotransformation, and drug biotransformation is going to be the basis of several types of drug-drug interactions. So that's what these two handouts are for. We will take a look at these. These little miniature case studies, by the way, I didn't make these up. These are from the literature. These actually happened. So sometimes physicians prescribe drugs and because the patient hasn't told them, oh, so-and-so prescribed me this. Oh, the corner clinic I went to for my sore throat gave me this, or I went to this person for my sore back, or, oh, I take this herbal supplement or something like that. Very often, if you're an OT or a PT, because you are putting your hands on the patient, your relationship with the patient is different, they're more likely to talk to you. Also, by law, before you can put them on the table, you have to have a list of all the drugs that they take. Now, Barbara Cliffmiller, who's a PT in Jackson, she sings in the chorale with me. She told me this story and she said, this is not uncommon. An elderly lady came in and she had a Ziploc bag of her medication. And so Barbara went through it as she was obliged to do by law, wrote everything down, and she said, Martha, what's this? It was ketamine. Oh, the vet prescribed that to my dog. It makes me feel better when I take it, and it's cheap, so I'll just take this. Unless you've heard, if you haven't heard about ketamine, ketamine causes hallucinations, particularly in people who are elderly. And yet this dear lady was taking her dog's ketamine. So I said, yikes. And Barbara said, that's a lot more common than you think it is. So very often it's not the doctor who catches these sorts of drug-drug interactions. It's actually the nurse, or it's people like you, health coaches, PTs, OTs, chiropractors, because chiropractors too, you have to know what drugs are on before they can get on your table. And they're more likely to tell you about that herbal supplement they take than they are to tell their doctor, oh, the doctor doesn't care about that. But with a little gentle questioning, you say, oh, yeah, herbal stuff. Do you have teas? And like that, because the doctor's not going to say teas. Oh, yeah, I take some St. John's wort. Helps my mood. We're going to say St. John's wort is a notorious drug interactor. So before we get into that, we'll talk more about phase 1, phase 2 reactions, and then get into the drug-drug interactions. But first, let's have a word of prayer. Father, thank you that it's a tad warmer today. We pray, Lord, that through you, we can continually offer a sacrifice of praise, that we can have lips that openly profess your name and not forget to do good and to share with others, because with such sacrifices, you indeed are pleased. Thank you, Lord. We pray that our lives indeed would be pleasing to you. In Jesus' name, amen. All right, so cytochrome P450 is, again, remember you have a handout that gives you a picture. First of all, you have a list of the different types of cytochrome P450s, pages 14 and 15. Remember, this is a gene family. Gene family. Is there anyone here who doesn't know what a gene family is? Okay, good. We all know what a gene family is. So these are genes that are very closely related. Sometimes they're even clustered on chromosomes. They very often result from gene duplication. The proteins they encode are not exactly the same, but they're very similar. And they tend to have similar, albeit not the same, biological functions. With this family of cytochrome P450s and their various isozymes, they can address very, very large number of substrates. So, and they're given these rather boring but easy to remember numbers: 1, 2, 3, 4, blah, 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 so on and so forth. And there are over 50 of these genes. And because of alternative splicing, they encode well over 50 proteins. So lots of different types of these, but they all have this feature in common. They're all iron heme enzymes. They catalyze a multi-step reaction. If you look at page 16 on your notes, that shows you the cycle of this. We'll come back to this in a bit. These require iron. So if your patient is anemic, their ability to metabolize drugs might be prevented, might be inhibited, might be decreased. So they're found predominantly in the liver, but they're also found in the small intestines. Those are the two main places they're found. Again, big one is the liver. Then they're scattered throughout the body, kidney, brain, so on and so forth. But the contribution those other sites play is pretty minor compared to the liver and the small intestine. These are mixed function oxidases. They use these niacin-based cofactors and a DPH, and they also use molecular oxygen. So this is a recapitulation in a little nicer form than what you see on page 16. I drew this myself, which is why it doesn't look nearly as pretty as this. But as you can see, the R, which is the drug in that case, it's a hydrocarbon of some sort. Brooklyn, do you have your hand up?
Yeah, the screen's a little.
Screen's a little cockeyed. Okay, let's fix that. Better? All right, good. There's this, so these, I always think, that puts a lot of glare on the screen to me. So we're just gonna do that. I think it lights up the room nicely, but you get this awful glary thing across. It's like having a window open, the sun goes right across the screen or something. So notice that the drug binds predominantly to the iron at the center of the heme group. And while it is bound to that iron, NADPH and molecular oxygen will derivatize it. It will put either a hydroxyl group on it, it'll make a ketone group, it'll maybe hydrolyze the molecule. The way the molecule gets derivatized varies, as we'll see, relatively widely, but this is a strategy that it uses. The iron goes from a different oxidation state, goes from an iron 2 to an iron 3, back to an iron 2, so on and so forth. And this is a crystal structure of one particular cytochrome P450. So the heme is right here, and the iron is that silver thing in the center. This green doodad there, that's actually camphor. Camphor is the stuff in Vicks Vapor Rub that gives you that, opens your channel. It's also in cough drops. Camphor, you can see, is bound to this particular cytochrome P450. That's a xenobiotic. So it's dealt with by cytochrome P450s. You have a channel over here. The drug essentially is able to come in the channel this way. Different members of this family have different shaped channels, so they can accommodate different sized drugs. And the heme, again, is kind of the star of the show. And the shape of this molecule is relatively similar in each of the family members. Now, these drugs are also embedded in membranes. They're embedded in the smooth endoplasmic reticulum membrane. And if you look at liver cells under a slide, I don't know if any of you have the experience of doing that, liver cells have lots of smooth ER. So you have lots of this enzyme. That's why drugs are predominantly metabolized in the liver. Many of the cytochrome P450s are inducible. That means if you take a certain amount of a drug, if you are exposed to a certain type of xenobiotic at a high rate, the degree to which the gene that expresses a certain cytochrome P450 will be upregulated, you'll have more of that enzyme. Good example, cigarette smoking. Cigarette smoking beefs up cytochrome P450s. It induces them. Not all cytochrome P450s are inducible, but many of them are, and we're going to see that certain drugs are inducers of cytochrome P450s. Also, these are encoded by genes. Those genes are subject to genetic variation from person to person. Some people will have alleles of certain cytochrome P450s that are poorly active. That means they will metabolize certain drugs poorly. Other people will have versions, alleles of these drugs that are more active. They'll metabolize these drugs faster. Other people will have extra copies of certain cytochrome P450s. That makes them rapid metabolizers of certain drugs. And now there are actually genetic tests that are commercially available for patients. So if they don't respond to a certain drug, some drug is it's toxic to them or something like that, what have you, you can actually have them tested. Insurance is just starting to get into the act to pay for these because these tests were experimental for a while. Insurance will not usually pay for something unless it's more mainstream. It's getting to the point where these tests are being used more and more. They're more and more reliable, and insurance is now starting to pay for them. Some drugs will inhibit certain cytochrome P450s. We'll have a look at those because if you take two drugs, one's metabolized by a particular cytochrome P450, but then you take another drug that inhibits that cytochrome P450. Now this other drug will build up in your circulation. It may cause side effects. And there's lots of different so-called isozymes. Isozymes are versions of a particular enzyme. They're very closely related, but they're slightly different. They're either the result of alternative splicing, or they may be encoded by two very closely related genes that may even be very close together in the genome. That's usually the result of gene duplication. So you have lots of different types of these genes in your body. What kind of reactions do they catalyze? Bit of a chemistry alert here. If chemistry makes you break out in a cold sweat, then steel yourself. For the next few slides, you're going to see some chemistry. And this is just to give you an idea of the types of reactions that these enzymes catalyze. So if we take this type of molecule, one of the potential types of reactions is so-called dealkylation, where the bond between these two, this oxygen between these two moieties is broken. And now you get these two molecules here. That's called a dealkylation. Notice you take the molecule, you break it apart. That occurs in some cases. The other is that you take this halogen and you can take that halogen and you rearrange this molecule up here and you replace that with a hydroxyl group. So this gets put up here and then you hydroxylate it. That's a so-called para-hydroxylation shift. Para-hydroxylation shift. These enzymes can do that too. Then you can have cases where this halogen here gets replaced with a hydroxyl group, or you just stick a hydroxyl group here, a meta-hydroxylation. Bang, you hydroxylate there, and now that has a hydroxyl group on it. Now, what does this accomplish? Well, hydroxyl groups make you soluble. So these molecules here are all more soluble than the parent compound. You can also add another hydroxyl group over here, a so-called ortho-hydroxylation. So you have para, meta, ortho-hydroxylation. So you can add hydroxyl groups at lots of different sites around this phenyl ring. You can do another para-hydroxyl shift by replacing this bromine over here with a hydroxyl group and then shifting that over there. And so on and so forth. You can shift this over here. You can do an ortho-hydroxylation shift. So you can rearrange, add hydroxyl groups, break the molecule apart. Every single reaction, though, makes the molecule more soluble. That's the thing I want you to see, is regardless of whichever of these reactions you do, the trend is you go from less water soluble to more water soluble. Sometimes you break the molecule apart. Other times you just add groups that make it more water soluble. If we consider other types of molecules, so sulfur-containing molecules can be converted into these sulfoketone type molecules. That's more soluble than this molecule. Nitrogens can undergo a nitrogen oxidation. That's more soluble than this. Double bonds can either be reduced or they can undergo epoxidation. Epoxidation can then undergo further oxidation so that you make it into a hydroxyl group like this. So these may end up going all the way to this here. But again, the trend holds. This is more soluble than the double bond there. Aliphatic molecules like this get turned into alcohols. This is more soluble than that. Aromatics, again, are hydroxylated. This molecule here, phenol, is more soluble than this molecule here, benzene. This is not a molecule you want to ingest a lot of. It's quite carcinogenic. Ethers, as you can see here, are broken apart, giving you two alcohols. Both of these are shorter and more water soluble than the ether. And then amines can undergo dealkylations, where you now end up with a primary or secondary amine and a primary alcohol. And then ketones, as you can see here, ketones can end up getting either dealkylated with the production of a aldehyde, or carboxylic acid in this case, or formaldehyde. Either what you say, then this double bonded moiety here, this alkene, that essentially can undergo epoxidation and then reduction to an alcohol. So all of these reactions here, they produce things that are more water soluble. Not all phase 1 reactions are dependent on cytochrome P450s. Most phase 1 reactions are dependent on cytochrome P450s, not all of them. You have enzymes really throughout your body that perform a wide variety of reactions. Some drugs will encounter these enzymes. Many of these enzymes are in the liver, but they're usually experience much wider distribution throughout your body. They can participate in phase 1 reactions as well. So there are several types of so-called oxidoreductases. It's a big group of enzymes. You have lots of these. And if drugs encounter them, they can be subject to oxidation. Now remember, oxidation involves the removal of electrons. In biology, when you remove electrons, you typically remove hydrogen ions too. So you're not just removing electrons, you're removing electrons and hydrogen ions as well. So your tertiary amines, they're going to be oxidized to amine oxides. Notice this molecule is charged. That molecule is more soluble than this one. Same thing with secondary amines. With secondary amines, you convert them to hydroxylamines and nitrones. Both of these are more soluble than the secondary amines. And the liver can do this, but so can other tissues as well. And then your hydrazines get converted also to amine oxides. Thiols, they get converted to disulfides. Sulfides get converted to sulfones, sulfoxides. Again, these are all oxidation reactions. They produce things that are more soluble than the original molecule, and then thiones get converted to the radicals here that is also much more soluble. So whether you contain nitrogen or you contain sulfur, these and the enzymes that carry these out are called flavine monooxygenases. Again, very widely distributed throughout the body. Amine oxidases can take amines. These are just a couple of drugs that have amines in them, and they're converted to aldehydes. Aldehydes are very soluble, but they're also very reactive. So this will then tend to react probably with water to produce, say, carboxylic acid or something like that. You'll then make ammonium. Ammonium will be converted to urea by the liver, also very soluble. Dehydrogenases, another big group of enzymes. Alcohols get converted to aldehydes. So your alcohol, if you have an OH and you are an organic molecule, you are an alcohol. Alcohols are converted to aldehydes, and alcohols themselves are pretty soluble. Aldehydes, however, will tend to have more asymmetry of electronic distribution and will be even more soluble. They'll also be more likely to be converted into something less harmful. So this could be the case with ethanol, can be the case also with propanol, butanol, whatever. These dehydrogenases are quite versatile. There are also reduction reactions. In this case, you're adding electrons. So azo bonds are things where you have two nitrogens and there's a double bond between them. That's an azo bond. And you have enzymes that are capable of azo reduction. So prontosil and tartrazine, they have azo bonds, and prontosil is the precursor for this antibiotic sulfanilamide. It is produced by azo reduction. So you get prontosil is a dye. You give the dye and then you get an antibacterial compound out of it. And sulfanilamide is not used anymore, sulfa drugs. Sulfamethoxazole and trimethoprim combination has replaced that. But this was the way essentially you made sulfanilamide. Other drugs, there's just a few that have these azo bonds in them. Besides our own enzymes, there are bacteria in your GI tract that can actually reduce azo bonds as well. And that's a strategy for drugs that you want to get to the large intestine, because you swallow the drug, the azo bond is not really digested in the GI tract until it gets to the colon. When it gets to the colon, anaerobic bacteria in the colon can reduce that, and then you generate the drug. That's a strategy that's used for certain types of colon-specific drugs. Pretty clever when you think about it. If that's the case with azo groups, what about nitro groups? There are drugs that have NO2 at the end, and here's just a sampling of some of these. The antibiotic chloramphenicol, nitrobenzene, that's a pollutant pretty much, but clonazepam is a benzodiazepine. And then that's a middle acting, it's medium acting, it's got a medium half-life. Then dantrolene, that's an important muscle relaxant, also a treatment for something called malignant hyperthermia. Those have nitro groups on them. And nitro reductases are done stepwise, but they give you this molecule that is a lot more soluble than this. So nitro reductions are done by several different enzymes. Carbonyls are reduced to alcohols. There's lots of tissues can do that. You have several drugs that have carbonyl in them. And then hydrolases, esterases. Your body is chock full of esterases. Esters don't last very long in your body. Let me give an example. There are certain types of local anesthetics. Local anesthetics, for example, that are used topically. So for example, Procaine. Procaine goes by the trade name Novocaine. Novocaine can't be used internally because lots of people are allergic to it, but it can be used topically. So you rub it on the skin, it deadens the skin briefly, gets absorbed in the skin, and it gets degraded lickety-split because your skin's full of esterases. That thing's an ester. And this entire group of ester containing local anesthetics, you inject them locally, but as they diffuse into the tissue, they're degraded very quickly. And you don't want them circulating throughout the body because they inhibit voltage-gated sodium channels. What would that do if they got to your heart? Would that be good for your heart? No. So you don't want them to get to your heart, but they never get to your heart because they're broken up so quickly, because your body has so many esterases in it. Amides are degraded by amidases. Amidases, again, ubiquitous throughout your body. And oh, look, lidocaine. Lidocaine is a topical anesthetic. There's a whole group of these topical anesthetics that have amides in them. And these amides, which are shown here, again, they go away from the area where you injected them. So mepivacaine, lidocaine, bupivacaine. Bupivacaine is the one that's used for epidurals when you give birth. And that's an amide. And when it diffuses out of the cerebrospinal fluid, because you don't have amidases in the cerebrospinal fluid, but you do once you diffuse out of it, it gets degraded because these enzymes are so widespread. So a few things that induce cytochrome P450s: smoking or eating charbroiled foods. So every time when Burger King does their commercials for the charbroiled Whopper, I always have visions. I know it's a very nerdy thing, but indulge me. I always have visions of induced cytochrome P450s, in particular this one. So if you eat bread that got a little too brown or maybe blackened, the toaster was set to potash instead of, nice golden brown bread, you're going to induce cytochrome P450s. Now, it doesn't mean that piece of bread will kill you, but charbroiled meats, charbroiled breads, they induce cytochrome P450s. Certain types of drugs, barbiturates, or the anti-tuberculosis drug rifampin, they induce other types of cytochrome P450s as well. Drugs can induce these enzymes. That's something to keep in mind. And then some of these drugs inhibit certain cytochrome P450s. Cimetidine is an ulcer medicine that's available over the counter. I'm trying to remember what it's called over the counter, but I can't remember. But it's been available over the counter for quite some time. Cimetidine is a pretty avid inhibitor of certain cytochrome P450s. The other group of drugs that inhibit cytochrome P450s are the so-called azole antifungals. And you know these drugs because they have azole at the end. So ketoconazole, fluconazole, itraconazole, vorconazole, posaconazole, your mother-in-law conazole, those are all azole antifungals. Those inhibit certain cytochrome P450s, and you need to watch for those. The other ones are these macrolide. Oh goodness, your professor needs to learn how to spell. Just take the O there and scratch it out. Antibiotics, not antibiotics. Antibiotics, they get converted to metabolites that inhibit cytochrome P450s. The biggest offenders are erythromycin and clarithromycin. Azithromycin, not so much. Then there's the newer one, telithromycin, which you should never prescribe if the drug causes liver damage. I don't know why the FDA ever approved it, but they didn't ask for my advice. A few words about phase 2 reactions. These enzymes are called transferases. So these take polar or sometimes charged molecules and covalently attach them to the drug or the drug metabolite. Because they attach these big, bulky, charged or polar molecules, they make the drug inherently more soluble. So these include drugs that transfer methyl groups. Now, methyl groups themselves are not very polar, but if you attach a fourth methyl group to a nitrogen, that nitrogen now becomes charged. You've made a quaternary salt. Quaternary salts are very charged. The most popular one is this one, glycuronidation. In this case, you take gluconic acid, which is the reduced version of glucose. You attach it to a drug. The gluconic acid is charged at physiological pH. It's big, bulky, charged, and it allows the moiety essentially to be excreted very effectively in urine. Acetylation, as you can see, is something that happens to nitrogen groups. Other types of molecules as well, that will tend to make nitrogens now more charged. Glutathione is a small peptide, consists of 3 amino acids. So you can buy glutathione, in fact, in health food stores. If you go into the Westwood Mall, Jackson Crossing, and you take the detour towards Target, on your right-hand side, there's a health food store, and there's a lady from my church who actually works in there. If you walk in there, we sometimes, in my research here, we've tested supplements and things. We tested, I don't think it's marketed anymore. Super Pump 250 is one of these ones that increases arginine levels. But it's a pre-workout, doesn't work. We tested that, and we tested some other supplements. The baseball team one year swore by vitamin B12. So we tested B12 supplements. They didn't work either. Although that was an acute feeding. Might want to redo that with a chronic feeding. So that might be a project for a student maybe who's enterprising and wants to try to see if B12 supplements help with hand-eye coordination or reaction time or something like that. Yeah, glutathione. You can, on the shelf, you can buy glutathione. There's really no data I'm aware of that glutathione supplements will help you deal with xenobiotics better, but some people say it does. So glutathione is something that's conjugated to molecules. Sulfate groups, there are sulfotransferases. Sulfates are big and charged. And then also the amino acid glycine is also attached sometimes. And glycine, again, has charged moieties, and that will cause the molecule also to be much more polar. Definitely the one that's used the most is this one here, glycuronidation. And to show you essentially where you put the glycuronic acid. So essentially here is the glycuronic acid. It's attached to a uridine diphosphate molecule. There's several. This is a gene family. The glycuronylyl transferases. They're usually called UGTs. You can see that glycuronylyl transferases didn't quite roll off the tongue. So there's a UGT 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's a lot of these. They handle lots of different substrates. So you can see they usually get attached to the hydroxyl group or to the sulfur or to the nitrogen or to the nitrogen here or blah, 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 blah. You get the point here. They're attached to lots of different places, and they make molecules that are potentially not very soluble, much more water soluble. Word about change in metabolism during aging. During aging, phase 1 metabolism decreases. Phase 2 metabolism does not. So it's best, if you were a prescriber, to prescribe medications that tend to be metabolized mostly through phase 2 reactions. And there are options for certain types of drug classes where you can say, you should probably be on this one, not this one, because this one is metabolized by phase 2 reactions, not by phase 1. You're older, your phase 1 reactions have slowed down. One of the blessings of getting older. Phase 2, however, they don't slow down as you get older. So something to consider. Now let's consider some of the genetic differences between different people when it comes to the functionality of these particular enzymes. This enzyme here, cytochrome P450 2D6, 2D6. There are 4 different classes of people when it comes to 2D6 activity. There's poor, intermediate, normal, which is also called extensive, and then ultra rapid. Poor, intermediate, normal, or extensive, and ultra rapid. 5 to 10% of the population are poor metabolizers. These people have alleles of cytochrome P452D6 that have no detectable activity. So they are poor metabolizers. When I use this term, everybody know what that term means? For anybody who doesn't know what allele means? Everybody know what that means? Okay, good. I'm just checking. One can't assume. So there are alleles of this particular gene that encode enzymes that just don't work. And 5 to 10% of the population have these alleles. So some people are deficient in this particular activity. Now, if you take this handout here, and Maddie, you weren't here to get this, but I'll put this online so you can download it. I'll put it under Blackboard so you can get it. If you look at page, no. Oh, crumbs. I don't have a list of 2D6 substrates. I'm sorry. I thought I put that in there. I'll just read you a few of the substrates of cytochrome P452D6. Lots of antidepressants are substrates of cytochrome P452D6. So are several antipsychotics. Another substrate of this enzyme, a group of drugs we will talk about when we get to blood pressure, beta blockers. Beta blockers. Many of them are substrates for 2D6. Several opioid analgesics are prodrugs that are activated by cytochrome P452D6. So those are several examples. Now, there are also people who have extra copies of cytochrome P452D6. Ultra rapid. This is 1 to 7% of the population. However, in people of Ethiopian and Saudi Arabian origin, up to 35% of these people are ultra rapid metabolizers, probably due to the types of spices they use in their foods. They're exposed to certain plant alkaloids very often that are metabolized by 2D6, so their bodies have adapted by making more of it. I don't know if any of you are fans of Middle Eastern food. Anybody? I love it. If you eat it, it's heavily spiced with very, very strong tasting plants that make lots of alkaloids, a lot of rosemary, lots of dill, those sorts of things, sage, and what have you. I have a buddy, actually, we were postdocs together at University of Pennsylvania. Amin, he works at the University of Elaine, and one of his research projects is he takes extracts of medicinal plants that are used in Saudi Arabian lore, and he tests them for anti-cancer activity and for hepatoprotective activity. One of our students, Madison Waldy, actually did a semester in his lab. He's at UAE, United Arab Emirates in Elaine. And he has a model where he infuses rats with drugs that give them liver cancer, but if he pre-treats the rats with the extracts from these herbs, the rats don't get cancer sometimes. And he has another model where he treats the rats with drugs that are anti-cancer drugs, and he pre-treats them with the extracts. If he does that, the rats don't get the liver damage they would normally get from these extracts. So Amir's got a very interesting model system, and he's been able to get lots of funding for that. And Maddie had a really great time in his lab. Yeah.
So looking at the different types of people, is 2D6 like fast metabolism and 2C9 just going?
No, all of everything I'm talking about is with 2D6. So 2C19, 2C9 have their own caveats as well when it comes to individual drug metabolism. So if I give you information that says this drug is metabolized by cytochrome P452D6, people are individuals, right? Some people may not metabolize it. You may give them a standard dose of that drug and it might be too much. They might have severe side effects because they don't metabolize it. Others, therapeutic doses, they may chew it up because they're ultra rapid metabolizers. Have to treat people as individuals, don't you? Depends on the drug. Depends on the drug. Some drugs, usually drugs are metabolized by more than one cytochrome P450, but there's usually a primary metabolizer and a secondary one. So if you inhibit one enzyme, the other enzyme will usually take over and do the job. For some drugs, however, there is one enzyme that specializes in that drug. And if you inhibit that enzyme, the levels of that drug will usually be just too high and the patient will experience side effects, like what we'll see with these case studies. So in these people of Ethiopian, Saudi Arabian descent, who are ultra rapid metabolizers, they will chew up antidepressants, antipsychotics, beta blockers really quickly. So standard dosages for these people won't work. You'll have to dose them up. Also, if you have opioids that are prodrugs and are converted into the active form by 2D6, standard dosages of these opioids can poison them. So these are considerations to take into account. 2C9, to jump down to the bottom, is a very highly polymorphic gene. Over 50 different alleles have been mapped. Some of these alleles have decreased activity. So there is an allele that is very common in people of European ancestry, which would probably, I'm guessing, be most of you in this room. So I'm Eastern European ancestry, well, Bradovich. I'm Croat. Most of you, I'm going to guess, are Heinz 57s. You're probably English, Dutch, Scotch, Irish, a little Italian, and then, maybe some Irish, whatever. You're probably mixtures of this and that and the other thing. I'm just going to guess. Now, Doolittle is very English, but England, you have the Saxons and they were invaded by the Normans. And so you have French as well. And then there's Welsh there too. So you probably had some Welsh. And then you had Germanic tribes that invaded too. So there's probably some Germanic blood there too. So, and then English might be from one side and you might have, Norwegian on another side. And if you're from Northern England, there's Viking in there too. So if you're English, you're a mixture inherently. Did I get it right? Yeah, it's a lot of everything. So, it just depends. So this particular allele that's found in Europe, it's called allele number 3. Really creative name. It will have a third of the activity of the normal enzyme. Then there's another allele that's called allele number 2. That has a fifth of the activity of the normal enzyme. So these essentially show really, really low activity. Now, 2C9 is the main drug that metabolizes the anticoagulant warfarin. And since you have an inability to properly metabolize warfarin, you're going to have to dose warfarin down in cases like that. That's just one example, essentially. And then there are alleles where people are completely deficient of 2C9 activity. And this is the case in people from who are of Japanese descent, and also of several other different types of Asian descent as well. These individuals are unable not only to metabolize warfarin, they have trouble metabolizing certain types of drugs for type 2 diabetes and things like that, and also for several types of anti-cancer drugs as well. Let's go back now up to 2C19. 2C19 is also a cytochrome P450 that is subject to a respectable amount of genetic variation. This drug metabolizes a lot of your proton pump inhibitors that are used for gastroesophageal reflux disease. It also metabolizes many antivirals, particularly anti-HIV drugs. Several anti-epileptic drugs are metabolized by cytochrome P450 2C19. And there are 5 distinct genetic polymorphisms. Several have normal activity. One of them has increased activity, but one of them has no activity. So about 62% of the population has normal activity, but over 15% of the population has no activity. And then 22% of the population has increased activity. And this is just the case with several of these enzymes. One other polymorphism that doesn't have to do with cytochrome P450s, it has to do with the enzyme that metabolizes ethanol, alcohol dehydrogenase. Alcohol dehydrogenase is subject to extensive genetic variation. Some people, now, when you take in ethanol, it's converted to a metabolite called acetaldehyde. Acetaldehyde is a metabolite that inebriates you. Some people convert ethanol to acetaldehyde very slowly. So they can drink quite a bit before they will show the effects of it. Others have alcohol dehydrogenase is extremely active. Therefore, they convert it to acetaldehyde very quickly, so they get inebriated really fast. You ever heard the story of, oh, some people, they can really hold their liquor? Like my family. Believe me, I've been to lots of weddings. I grew up on a grape farm where the fruits of the vine flowed freely. My family can drink a lot before they feel it. So my heritage, I come from a long line of grape farmers. Our particular allele of alcohol dehydrogenase, we metabolize it slowly. Whereas I used to work on my dad's farm. Most of the people in the fields who worked with me were of Latin American descent. They used to tell me stories and say, oh man, 2 beers. And I get crazy. I said, 2? That's all, yeah, 2. In fact, 1, after 1, I'm really feeling it. And 2, I just get crazy. I have a lot of fun. I don't remember it though, but I need to, yeah, 2. Really? Yeah. Does that run your face? Yeah. Yeah, my brother, same way, so on and so forth. And people of Mexican descent, particularly Amerindian descent, because they're Spanish and Amerindian, Amerindians in general, they tend to have very active alcohol dehydrogenases that convert alcohol to acetaldehyde very quickly. So it doesn't take much for them to start being affected by it. Now, that doesn't mean people in my family should have several beers and then drive home. No, 1,000 times no. But it does mean that the tendency for you to be affected by something like that, I'm not advocating drinking, okay? I'm not telling you about the biochemical fact of your body, and that biochemical fact is due subject to genetic variation. This is well documented in the literature. Okay. Okay, other things that can affect it. Smoking, of course, we talked about that, grapefruit juice. Grapefruit juice, if you go into retirement homes, there will be a sign in some of them that say, in fact, the Ganton one, the Alzheimer's one over here. You've been in there, you've seen it? Yeah. Bree, you worked as a CNA, you said. If you've seen that up in the places you've worked? The hospital, okay. You worked at the hospital. Okay. You may have seen on the paperwork, no grapefruit juice. Yeah. There'll be signs that say no grapefruit juice because many of the residents are on medications whose cytochrome P450s are inhibited if they were to drink grapefruit juice. So grapefruit juice is a pretty potent inhibitor of a major cytochrome P450 called cytochrome P453A4. Milk thistle. Milk thistle is taken as an herbal remedy by some people. It inhibits phase 2 reactions. Phase 2 reactions. And then St. John's wort. That sounds like something from Harry Potter. St. John's wort is an herb. It's a mood stabilizer. Very, very popular. This is a notorious inducer of cytochrome P450s. It's usually taken by people who are prone to depression, who tend to feel blue. There's been a lot of work on it. It is very effective for mild to moderate depression. But if someone's on it, they have to tell the provider. Otherwise, you're going to have a lot of drugs that don't work. Males will tend to metabolize drugs faster than females. Older people for phase 1 reactions will metabolize more slowly than younger people. Babies, in some cases, will not metabolize certain drugs at all. Therefore, for babies, there are certain drugs that are just don't go there. Barbiturates, for example, you never give babies barbiturates. Never. They can't metabolize them. They'll build up in babies and they will cause the baby to be so severely sedated they won't feed. Okay, drug-drug interactions, inhibitors, inducers. Take your handout and let's take a look at case study number 1 here. I'll just do this one here to give you an example of how this might work. All right, so we have a patient who is an epileptic and is on this anti-epileptic drug called phenytoin. Phenytoin goes by the it's not Depakote. It's it's Depakote. Depakote, I think. And say this person has really bad ringworm. So this person gets prescribed fluconazole, which is available as a pill, essentially, for ringworm, diflucan. So they take oral fluconazole while they're on phenytoin. Now, azole, fluconazole. Fluconazole is a pretty potent cytochrome P450 inhibitor. Turns out phenytoin, if you take a look at your other handout, and you take a look at the substrates, yeah, page 3. So take a look at page 3. And so if we look at page 3 and we look at substrates for 2C19, take a look at the P's under substrate, what do you see? It's not Depakote, it's dilantin. Right. Yeah, no, terrible track. So phenytoin is a substrate of 2C19. Turns out that 2C19, it's not in the list there, but it is an inhibitor, fluconazole, inhibitor of 2C19. So it is an inhibitor of 2C19. Your phenytoin levels now spike in the body. And the day later, the patient suffers from nausea, slurred speech, and a lack of motor coordination, otherwise known as ataxia. Those are side effects of phenytoin toxicity. So the phenytoin levels, they're within this window, you get good treatment. You inhibit 2C19 and now phenytoin levels spike and you get toxicity. See how that works? So probably what happened, this person went to a walk-in clinic, didn't tell them they were on phenytoin, just said, it itches, please help. And the clinician who wants to help probably looked at it and said, that's ringworm. I can give you fluconazole. The oral tablet is cheap. If your insurance may not pay for it, you can get this pretty cheaply. Pharmacy's just down the hall. Oh, you on any medication? Not really. Nothing important. You sure? Yeah, I'm on it. Okay.
So if any one of these inhibitors in table 2 are combined with one of the substrates in table 1, will the substrate spike cognitive toxicity? or-
Potentially, yeah. Yeah. Now, pharmacists will enter the drug into a program. There's several different types of programs that will detect drug-drug interactions. There's Spires and there's several others. I forget the one they use at WeatherWax. But there's a bunch of them. What do you guys use in the hospital? Do you use Spires? You know, you're trying to push EMRs out of your mind because they're such pains. And that's essentially how they can pick these up. Again, sometimes the patient doesn't tell you what they're on, and sometimes records are not up to date. Case in point. So we have access to our own records through MyChart. I have stopped taking a multivitamin. I've taken a multivitamin now in over a decade. I've gone in and I've corrected it probably 12 times. They still have on my chart that I take a daily multivitamin. I keep, every time I go in for physical, multivitamin, I keep saying, no, expunge it, take it out. Please, I don't take a multivitamin. Correct that, please. It's still in my chart. So given the way records are, this sort of thing may not surprise you, actually. All right, we are out of time for today. We'll pick this up and we'll work on these and we'll get some examples. And this is a little pharmacological humor for the day. And we'll start with this. Propecia is a hair growth. It's for baldness. So Viagra, you know what that is. So mixing Viagra with Propecia and that's your result. So.
Just the transformation stuff.
And also the pharmacokinetics. Yeah.